Hello, dear classmates. Welcome back to the logic simulation. In this video, we are going to introduce simulation models. We will introduce logic states and how we evaluate logic gates, and also we will introduce delay models in logic simulation. When we talk about logic states, you will think that there should be only two states in digital circuits, right? 0 and 1. Well, this might not be true in practice. In practice, in a logic simulator, we need to consider not only 0, 1, but also a third logic state, which is unknown. So we would need ternary logic simulation. This was proposed as early as 1965. The unknown value U means that the logic value cannot be determined at the time of simulation. Somebody also used the symbol X. In this video, we use the symbol U instead of X. Besides three-value simulation, somebody also need four-valued logic to represent a logic circuit state. The letter Z represents the high impedance state, which means the circuit node is floating. It has no conducting path to either VDD or GND. The following table shows a four-value logic truth table for an AND gate. Suppose that one of the gate input is 0, then the output would be 0, regardless of the other signals. This is what we call a controlling value. Suppose that in other case, one of the input is unknown and one of the input is in high impedance state. The output will be U, which means unknown. Please do not get confused by U and Z. They are different. Because the output of an AND gate is driven by this AND gate, so the output of this AND gate should be U instead of Z. The reason why we need so many logic states is to have more accurate simulation result. Of course, the penalty is that we will need more CPU runtime to run this simulation. In the ternary logic simulation, things becomes more complicated than we thought. Given this circuit, we have three primary inputs, A, B, and C. We have one primary output, which is K. For gate G2, A1, A2 are the gate input. F is the gate output. Please remember these acronyms, PI, PO. They will be used again in our future lectures. In this example, suppose that A input is 1, B is unknown, C is 0. If we run this simulation, the output of G1 is unknown, and G2 gate output is unknown, G3 is unknown, and finally the primary output is unknown. However, this is not an accurate result. Actually, no matter B is 0 or 1, the output K should be always 0. This is because of the fan-out reconvergence of the same signal B. You can check the correctness. If B is 0, we have this case. If B is 1, we have this case. No matter which case it is, the output should be always 0. So the unknown simulation result is actually not very accurate. One possible solution to solve this problem is to introduce a symbol U prime to represent the inverse of U. So now we have U prime at the inverter output. If we take the NOR of U and the U prime, we will always get 0. This sounds a very good solution, right? So what's the problem with this solution? In practice, there are many different sources of unknowns. For every different source of unknown, we would need one unique U prime. So there are too many U's needed in this case. We need symbolic simulation to distinguish all different sources of unknowns. Symbolic simulation is out of the scope of this lecture. So if you are interested, please refer to other books. The moral is that simulation results are not always accurate. We need to check it very carefully. In full value simulation, we need the high impedance state Z. High impedance states are often seen in the tri-state bus driver case. This triangle represents tri-state bus driver. When the enabling input E is 1, the output is equal to the input. When the enabling input is 0, the tri-state buffer is in high impedance state, which means the tri-state buffer is not driving the output. As we can see in this example, we have 3 tri-state bus drivers driving the same net Y. Only one driver is supposed to drive the output at the same time. So E1, E2, and E3 are called one-hot signals, which means only one at a given time. In this example, only tri-state buffer G1 is activated, and the input X1 is driving the output. So Y is equal to X1. The other 2 drivers are in high impedance state. So here is a small quiz for you. What if E1, E2, E3 are not one-hot signal? For example, 2 of them are 1 at the same time. Input X1 is 0 and the input X2 is 1. What happened to the output Y? Yes, you are right. Because we have conflict of signal, so the signal Y is unknown. Next, we would like to know how to evaluate a logic gate. A simple idea to evaluate a gate is to use the truth table. We can determine the gate output value based on a pre-stored truth table. For example, the following shows 4-value logic truth table for AND gate, OR gate, and the inverter. So now, what is the size of truth table for an input gate using 4-value logic? Yes, you are right. It's 4 to the power of n. This is exponential, right? Exponential size is very expensive for EDA simulation. We cannot afford to have such a large table in our computer memory, especially when n is very large. So in practice, we will break an input gate into multiple 2-input gates, and we use for loop to evaluate the gate one by one. So truth table technique is not very good in terms of storage size. So let's change to input scanning technique. The idea of input scanning technique is that we check the gate input one by one, and we determine the gate output by counting the number of controlling values C, inversion I, or unknowns. Each gate can be characterized by a controlling value C. Controlling value means the input value that decides gate output regardless of the other gate input. As we mentioned earlier, the controlling value of an AND gate is 0, and the controlling value of an OR gate is 1. The inversion value I is 1 when the gate output is inverted with respect to the gate input. Otherwise, I is equal to 0. For AND gate and OR gate, their I values are 0. For NAND gate and NOR gate, their I values are 1. This flowchart shows the input scanning algorithm. At the beginning of this algorithm, U_in is a flag which represents whether there is a known value at the gate input. The initial value is false. And then we check each input one by one. If any of the gate input has a controlling value, then the output must be C inclusive OR I. This corresponds to the first row in this table. As long as there is any controlling value, we don't care what the other values are. The gate is evaluated to C inclusive OR I. If there is no controlling value, we would check whether there is any unknown value at the gate input. If there is one or more unknown value at the gate input, we will set the flag U_in to true. After we check all the gate input, we will see whether all the inputs are C'. If all the inputs are C' and there is no unknown, the output will be C' inclusive OR I. This corresponds to the second row in this table. Finally, if there is one or more unknown at the output, then the output is unknown. So this is basically what the input scanning technique does. It counts the number of C, I, and U and determine the gate output accordingly. Now we move on to delay models. In a logic simulator, we need to consider both gate delay and the wire delay. In this video, we will focus on only the gate delay. Please refer to other textbook for the details about wire delay model. In gate delay model, the propagation delay is also known as the transport delay. The definition is the time from gate input change to gate output change. There are several different propagation delay models. For example, zero delay means that the propagation delay of all gates is simply zero. Unit delay model assumes that the propagation delay of all gates is the same, 1 time unit. The multiple delay model assumes that the propagation delay is multiple of some time unit. And finally, if we want to have more accurate simulation result, we can have several separate rise time and fall time. In addition to the propagation delay model, we can also apply the ambiguous delay model. Instead of a single propagation delay number, the ambiguous delay model assumes that the actual delay number is between the max value and the mean value. Sometimes we also use a typical delay or nominal delay to represent the average delay value. The third delay model, inertia delay model. Inertia delay means the minimum amount of time during which a signal must persist at the gate input in order to change the gate output. The inertial delay model considers a real situation where a short impulse at the gate input cannot generate any output change. The reason why we have so many different models is for different simulation usage. So let's now see an example. Suppose we have an OR gate where A is tied to 0 and the waveform of input B is like this. We have a rising transition at time 0 and we have a falling transition at time 2. Suppose that the propagation delay is equal to 3. In this case, the output C would be like this. The rising is at time 3, which is 3 time unit delay. In the second case, let's consider different rise delay and fall delay. Suppose the rise delay is 1 and the fall delay is 2. So the output C would rise at time t1, but it falls at time t4. So the pulse width is getting longer due to the difference in the rise delay and the fall delay. In the third case, let's consider the mean delay is 1 and the max delay is 2. So the rising time can be between T1 and T2. The gray box between T1 and T2 means that the output is unknown between this period of time. In the fourth case, let's assume that the inertial delay is 3. If we look at the input waveform, the pulse width of this input is 2, which is smaller than the inertial delay 3. So the output would not respond to this short input. In the last case, let's assume that the inertia delay is 1 and the propagation delay is 1. In this case, because the pulse width is 2, which is larger than the inertia delay 1, so the output would change at time 1 and it falls at time 3. In summary, in this video, we have shown 4 different logic states: 0, 1, unknown, and high impedance. We also introduced 2 different logic evaluation methods: truth table technique, input scanning. And we introduced propagation delay, ambiguous delay, inertia delay models. Now it's time for FFT. If we change from truth table to input scanning technique, what do we gain and what do we lose? You can consider the answer using CPU time and a memory trade-off. FFT number 2. In this figure, we have a pull-up or pull-down device. So, what is the use of this small device? You can consider the situation where E1, E2, and E3 are all zeros. Okay, thank you.